The topic of today is again the embedded programming. Last class we talked a little bit about what is embedded C, what does it mean to run it on the microcontroller, some tools such as static analysis and deoxygen. So today I'm mostly going to be talking about the first thing will be code repositories, which is a very convenient way to track your code, track changes, sort of avoid the problem where you had something half working, you make a bunch of changes and it doesn't work at all and you can't go back. So it's a really useful tool that you can use in your development here, and as well as debugging strategies. And the debugging strategies will be a little bit of what you'll see in the lab today. All right, so source code management. So if you've ever had work, you've probably hopefully had to work on group projects already now, or even on yourself. Half the time what you end up with is there's like 20 versions of this file, and you make a version, and then it's like, oh well, here's the May 5th edition, here's final, and then someone makes changes and say, oh, final 2A, stuff like that. So it's crazy, and you're doing this because you want to keep track of I made this this version and I want to save this in case I need to go back to it. So a better way to do this is what's known as a repository, and this gives you a central code base. So you can see what changes between versions of the code. So you can always go back in time and say, oh well, on May 5th, here's the version I have. We then made these changes, these changes, these changes. So that's one aspect of seeing what changed between versions. Another big thing is it lets multiple people work on this together, and some people can change one aspect of within a file, change part of a file where you're changing another part of the file. This is all really designed for code, so this doesn't work as well with a file format like a Word file. That's a really special format, but it works great with stuff like source code. There's a lot of other features that you can see. So one of them is something called branches. And I'll try to show you very briefly what this means. But basically, it's that if you have some code and you have a crazy off-the-wall idea and you say, hey, I'm going to try changing a whole bunch of stuff, you can actually make a copy of it at whatever the state was, make those changes, try it, and if it doesn't work, you can just throw those changes away very easily, at the same time as keeping a copy of your original code that someone else can be fixing other problems in. So there's a lot of hand-waving there. And what I want to do is show you how it sort of looks in real life. So I'm going to be using something called GitHub. Git is a type of repository. So this is just a format of it, or also known as revision control. And GitHub is just a website I'm picking that's quite popular for doing this. I'm going to be using a web-based, on the website, the web-based thing, and also this Windows client. There's what's called a GitHub Windows client. It's a specific implementation of a standard protocol. There's a whole bunch of different tools you can use to interact with it, and I can't try to show you every single tool. So I'm just going to show you some of the easier ones, in my opinion. So what this looks like to start with is you need to know, what does a Git repository look like? Come on in. So what a Git repository looks like is we have a list of changes. So if I look at, this is a project I'm working on, and we can see, for example, that every so often I just have these notes about what I've changed. If I click on one of these changes, so I say, fix whatever this decryption example, and you want to say, hey, what did I fix on that day? So you can just click on that, and it's giving you what's known as a diff, and the diff is showing you the changes between two lines of code. So in red with the negative, I've deleted this line, and then the positive is I've added this line. So you can see all I've done is I've changed, there was a C that changed to a P if you look really closely, and then there was possibly another change, I think, no, that was it. So now I can both look back in time, and I have a little note, this commit note that says, hey, why did I make these changes? And you can go way back in time and say, what's another change? Fixing issues. And again, I can look back and say what all did I change. So here I have this thing where maybe I had a wrong function call. It previously said str.toLower, which is some function, and I changed it to .lower. So this is what the revision control will give you. And if you want to play around with that, so the easiest way to do is if you go to GitHub, and these changes, by the way, so GitHub gives you a web-based thing, so I could look at the same thing online and see, what's the list of changes I've made, and it'll highlight, hey, here's what you did, and I can just scroll down. The same sort of idea, then minus and plus. Now, rather than using the web-based thing, what you can do is download this GitHub for Windows. So this is a client. You log in, and let me pull it up. And it gives you this screen. Get started by adding a repository. So the repository will be our source code that we want, like for a robot project. So let's say I have Colin's Amazing Robot. That'll be my repository name. And under here, there's something called git ignore. And what this is doing is this is ignoring certain types of files. These are files that you don't care about. So when you're compiling your source code, it's going to generate all sorts of files you don't care about. I don't know if it actually has stuff for the AVR built in, but there's sort of generic ones for C that you could set up. That part doesn't really matter. All that matters is you get a repository with some name, hit create. And there we go. So what this is if I look at the repository, I can open it in Windows Explorer, and it's just a directory. So I could make folders within here. So I'm just going to make a folder. So you could copy your whole, if you had an Atmel Studio project, you could just move the whole project in here. And let's call it C source. Oops, 3. I'm going to leave the 3 on. Some file. So I've made a C file, and I'm just going to put something in here. Hello world. Oops. Did that save? Yep, so that saved the file there. So I have this file. So now we'll do what's called our initial commit. So the commit is where we look at our hard drive and we publish everything into the repository. So we can look at uncommitted changes, and you can see that it's saying, hey, you added this file with these contents to it. And all you have to do is you can write a summary of what your changes are, and then hit a button to add it to your repository. So I could say, new amazing file. And just hit commit. And now we see that the summary of what I did, and it has that file. If I go back and say hello world to hello class, so I've made some change to the file, and again I can see, hey, uncommitted changes, and it tells you. So the other useful thing is if you ever wonder, oh, what did I all change in my my source code? You can really easily see the difference between files. So I'll say, change world to class. Hit commit again, and now we can go back and see, this new change was now says hello world, or hello class. It used to say hello world. And if you want to go back, for example, to this, so if I say, okay, my latest changes were crazy, that was not what I wanted to do, there's a way that you can revert back to it. So there's a button up here that says revert, I believe. Oops. Yeah, so then you end up with conflicts you have to fix. Let's just see. Uncommitted. Oh. There we go. Update. So everything should be synchronized. Oh man. So sometimes the demos don't work properly on you. But you can see the basic idea is it's at least keeping a track of every change you make. If I publish this to the online repository, it will also do the, you'll be able to see it. If I logged into my GitHub online, you can see it all there. So that's sort of a really quick, I don't have time to go through everything with GitHub, but if you're interested, I really encourage you to either download that and play around with it, or and look at these tutorials online. So I think that link is to one quick tutorial I had made on Git. There's a whole bunch of them. It's a really popular tool, and if you haven't used it, it's something that you're almost guaranteed to find a use for in projects you do both here and professionally. All right. So, debugging. So debugging is sort of how we fix things. Ignore that crazy screen change there. So there's a joke that says debugging, which is finding errors in what you wrote, is about 2 times or more harder than actually writing it in the first place. So if you ever write your cleverest possible code, you say this is as smart as I can be when I write the code, you are by definition too dumb to fix that code if there's problems in it, because it's so much harder to debug than it is to write. As a side note of that, that's half a joke, half the truth. Don't write overly complicated code. If you write code that you've tried to be as clever as possible, you're going to get into the situation where you look back at it in a week, 6 months, a year, and you have to say, oh, what was I thinking when I wrote this? So you're better off, and especially in this course where you have a lot to do, a short deadline, to have this really simple code that works well, rather than complicated code, that sort of vaguely works or has some weird bugs you can't find. So this will mean, keeping the C syntax as clear as possible, avoiding trying to compile, put everything together, stuff like that. So it's really important to write straightforward code that you can understand, and this will help you when you go to debug it. So when we say bugs, we always mean problems in the software. The actual name, calling them bugs, came from, I think it was in the 40s or 30s. It's been around for quite a while. There's sort of a story that the first case of an actual bug being found was in a computer when they were using relays and stuff like that in the computer, and they actually had a moth in the relay, and that's what caused the system to fail, is a bug in the system. And it was taped into their logbook, here's a log of what happened. This moth was in there. So that was, I forget when that was done in, but that's sort of what we mean by bugs. So debugging is getting rid of them. And if you had bugs in your house, you could use RAID or something. We need better tools than this to get rid of our bugs. And I'm going to talk about 2 of the main tools that you will have access to. There's some more advanced ones that we won't really use, but I'll very quickly mention them. And those will be, I think way at the beginning I had listed. Yeah, so blinking lights, Printf, this is the main one you'll use. And there's another option, which is what's known as an in-circuit emulator, or ICE, which will give you really in-depth debugging information about your device. All right, so the general philosophy we're going to look at is you should always, at first have an idea what the program should do. And I don't mean necessarily by this, oh, it should blink these lights, it should drive straight, turn right, turn left, stuff like that. I mean in terms of the program running on the microcontroller, you can say it should read this sensor at this line, the return value should be between 1 and 25. So you want to have a very good idea of what the program should be doing, what the value should be of your code. As part of this, you're going to determine the assumptions about how the program should be doing this. So how the program should be doing this means stuff like the microcontroller is interfacing to the timer circuit on the microcontroller, and I'm assuming that the microcontroller is running an interrupt every 100 hertz or something. So I have some assumptions. I'm always going to be making some assumptions that I did this correctly, and therefore the microcontroller is doing this. Or I'm assuming that I make this call to a function and it reads the sensor, the range sensor, and returns that value to me. I initially might not be checking that all of these assumptions are right. But I'm then going to check them by determining what it's actually doing and testing these assumptions. It's almost always there's some problem in what we assume the software is doing to what it's actually doing. And this is where most of the time you'll find all your bugs is just figuring out these assumptions and testing the assumptions and going by step. And using this, we can determine where things go wrong. And this is the case both for bugs that are related to, your coding has errors, syntax errors in it, problems with you've misunderstood the data sheet, and even more complex problems like, a pin on the microcontroller wasn't set up properly or there's a hardware short on the device. So bugs can come in a lot of formats and there's a lot of reasons they might exist. So you want to really get to the root of what's causing it. So to give you an idea of debugging a really simple program, let's look at this. So I have this program here, and what it's supposed to do is you see there's a while loop. This line here, oops, on the top, we have this if statement, and it says if pin D, so I'm reading in the value of the port register on the AVR, and I'm checking if bit 1 is set. So I'm going to get in a value that's 8 bits, and I want to check if this bit is set. So all I'm going to do is I'm going to AND it with 0000001. I'm going to AND it with that, and I'm going to see if the bit's set in the end. If the bit's set, I'm turning the LED on. So I have this macro here that turns the LED on. And you can see that all this macro does is set one of the port pins to be an output and then turns the port pin on. So the data direction register, if you've used the AVR stuff, means set that bit to output, and then now that the bit's an output, we can set it high. If I compile this and run it, and I said I put an LED on the board, with that pin being held low, so I'm somewhere port D0 is here, I've pulled it low, but the LED is sort of lightly on. If I pull that pin high, it goes really bright. So something's gone wrong. I know for sure that that port pin something's happening. The LED is not off. So there's a bug in here. And how can we find that? Well, using the same thing, we say, well, what do I think the program's doing? The program's reading in a pin and turning on an LED. There's basically two assumptions I'm making here. Assumption number one is that this if statement, is, or maybe three assumptions depending how you word it. So I have an if statement if the pin is high or low. So one possible problem is maybe I'm reading the pin wrong. So I need to figure out a way to test if I'm reading that right or wrong. It's a little tricky because even our LED, like normally we might use the LED for debugging, as we'll see, but even that's giving us a problem. So assumption number two is that LED on macro turns the LED on. So we have this, and we're assuming that when I call that, it turns the LED on. There's sort of a third assumption, which is that I assume that this is only executed when that if statement occurs. That's more along the lines of the language, so you might get too far down the path there. But we have sort of two assumptions we can fairly easily test right now. So the first thing I might do is I could comment out everything in that while loop. So, and you'll also need, a semicolon there. And I could say, well, if I comment out everything, I expect the LED to be off because I was assuming, the LED should be off initially. Maybe the LED starts in the on state. So the first thing I'm going to check is, was the LED off? That was one of the assumptions before anything happened. I compile this, download it. The LED indeed would be off, which I don't have a photo of, but it is. So I can sort of just slowly go through adding the original code back in. And this is where, when I talked before, we always try to reduce things to the minimum possible code sample that causes the problem. So in this case, if I do this if pin D is 1, so all I'm testing is, does it read that pin in correctly? And I'm not even seeing what it does because I have no way to see the return value. All I've done is this continue statement here means that the loop will keep going. But I'm just trying to get back to the stage where, hey, when I power it up, that LED sort of, does this weird half turn on, like this. So something's amiss here. And if I do this, it again works fine. The LED never turns on. So that LED on call doesn't happen. If I put the LED on call back in, I end up again like this. And once again, you have the problem. So this tells you sort of, or this forces you to figure out that there's some sort of issue in that, what I've written as a call here, but what's really a macro. And what that ends up being, at this point you sort of have to look at it a little bit, is when the compiler is inserting these, taking this macro and inserting these instructions into the source code, there was a bug inserted because this LED on actually just copied these two registers here, and the if statement is only applicable to the first of those two things. So when I have the C code, let me just open this. Oops, come on. So when I had the C code, if something, do something. We can do this in C, so if something's true, do something. And this is always just a single instruction. The problem is that what I had was this LED on. And LED on was actually a macro like this. Oops. Should be port B. So LED on was actually a macro like this. And so all the compiler does is it took, this stuff here and copied it in, and this of course should be LED on. So in the process of copying all that stuff in, what's actually happened, so that's what the compiler sees, and the if statement only took effect to the first part of that statement. So this was outside the if statement, so the port B or equals the one shift left 1 was always executed. For the AVRs, this means a not very strong pull-up resistor, very weak pull-up resistor is enabled, which is what turned the LED very lightly on. So this is what the compiler saw. So there's no, the debugging hasn't directly told us this, but it let us know the problem is as soon as we introduce that LED on macro back in. At that point, you know where to spend your time sort of looking more carefully, thinking, or asking someone, hey, what's wrong with this code? Without having done that, it's, you have to spend your whole time looking at a larger chunk of code. In this case, it wasn't a huge chunk to start with, but if you have a very complex program, this will save you a lot of time. All right, so going back, the two solutions are to just add braces around the if statement, and so now the if statement's constrained to include everything inside that macro. And this is one reason why it's always good to use these brackets, when you're writing C code to avoid problems like that. Of course, I also could, and you could do both of these, add these brackets right to the macro. So this way, no matter how the user, which is you, uses that macro, it's going to be pulled in with the brackets constraining, hey, I want this whole thing to be executed as one, treated as sort of one statement. So that's the second fix to that really simple bug. And again, the root cause was that this line being executed caused the pull-up enable on the AVR. So besides that really simple example, general hints, and you're going to have to spend a lot of time debugging, you just accept that. Don't spend a long time really staring at the code to find the missed brackets, semicolons. If you're just looking at our buggy code again, it's too hard to know where the problem lies within this. So you can take a quick look through to see if there's something that looks amiss, but if you just start staring at the code, it's going to be harder to find the root cause. You really need to write down your assumptions and then figure out what you've proven to work and what is unknown. Why it's useful to write it down is that you may go back. It might be a few hours later, you go back and say, oh wait, was that port, did that part actually work? So if you write down what your assumptions are, and then you write down, hey, I know for sure this part of the code is working, you'll never have this problem of trying to go back and trying to refix your mistakes. The other thing is that debugging is to some degree a creative aspect of it, and it is really helpful to take breaks. So if you're working for a while down in C102, go for a walk or go grab some food or something or talk to someone about it. The change of perspective you'll find is very, very useful. You could stay up really late and you'll just keep rehashing the same ideas. If you go to bed and get up and come back, the problem might be obvious. This is kind of how it always tends to work for me as well, so that's why I encourage you to use the chance to sort of get a fresh perspective. All right. So any questions on that part of it before I go into some simple examples of debugging? So what might you use for debugging? So say you had this code that you're trying to fix, and basically we have, read sensor is equal to, if this returns 0, drive into wall, otherwise drive left. So there's a lot going on. It's a simple statement, but this could mean have a lot of chances for bugs, because it could be, hey, there's a problem in read sensors, there's a problem executing drive into wall, and there's a problem executing drive left. At this point, we need to figure out, where does the problem lie? Is it in read sensors? Is it in drive into wall? Or is it into drive left? And with LEDs, the easiest way to do this is you physically add some LEDs to your board that you can turn on or off. And we simply turn them on or off at various parts in our code. So you see what I've done here is I've added, turn on this LED or turn on this LED. So obviously you want to make sure your LEDs work. But at this point, we can get an idea for where the code's executing. And of course, instead of LEDs, you can use stuff like the scope to see where, if you've got a lot of quick pulses, so you can see how often is this being executed and things like this. But the basic idea is that we're just going to turn on an LED, and I don't turn it off anywhere, you can see. So once it's on, it's on. And we can get an idea what our code is doing. So at this point, we can say, hey, is it the case that read sensor is always returning 0? And that's the problem. So if I only ever see LED, the first LED being turned on, which is with index 0, I know this code branch is always executing. Or it might be that it's the other code branch, or they get executed equally, and the problem is inside one of these functions. So if it's inside one of the functions, all we would do is, we would look into the read sensor function, and we do the same thing. We'd say, okay, I'm going to put LED on, turn the first LED on at the beginning, and turn the next LED on somewhere later down in the function. The idea being to slowly work out at what point does the program flow not match our assumptions, so not match how we think it should be executing. So that's a really, really simple way of debugging. It's limiting because, this read sensor, what if there was 20 possible return values? It's going to take quite a bit of work to figure out what the actual return value was. So, you could put a bunch of LEDs and turn them on in a special pattern or use blinking, which people will do when there's no other choice. But you really, really don't want to be doing that because it's a lot of work and it's hard to figure out what's happening. So what we're mostly going to be using here is what I call Printf debugging. And this is pretty common in a lot of embedded systems because you almost always have this capability, even if you have nothing else. So what is printf? Printf is in C what prints to the screen. You see the hello world program I used before, and it printed hello world to the command line. And we can use this to print all sorts of variable values or anything else. And that's what makes it really useful to us, is we can print the value of stuff that we're using. So we can read sensors, confirm the values being read, etc. As an example, here's printf usage. So hopefully you've used printf a little, but this is just a quick review. So basically we have this first part here is what's known as the formatting string. So we just have a string, and everywhere we have these %s signs or % signs, This is indicating that we have the value of some sort of variable to insert in. So %s here is a string, so we can see the formats listed, a few of them here. %d is an integer, and %f would be a floating point number. Using printf, you can introduce bugs if you do this wrong. So if I had %d here, for example, printf will not print a correct value. It'll print some garbage because it thinks it's an integer value when I've passed it a string and stuff like that. So of course you have to make sure you don't introduce bugs with printf, but that should be a lot easier to check through carefully to make sure you don't. Now the problem is on a micro, you just have this little black package with pins. Where the heck does printf go? So there's no screen here that it's printing to. We can still get printf and we can still use it though. And what we're going to do is use the serial port protocol, or use the serial port on the computer to receive this data. Very briefly, serial port is, and there's a link here that has a lot more information on serial communication. If you haven't used it before, is useful, but I'll just quickly mention the basics. When we say serial port, all we mean is we're using a serial protocol. What serial protocol means is if we wanted to send 8 bits of data like this, so you can see I have these 8 bits of data I'm trying to send from device A to device B. With a parallel protocol, it just says AMB at the bottom, I'm sending all 8 bits at once. And there's this clock here. The clock goes high, that says, hey, there's new data available. So this would be parallel. The other option is to do this serially. So in serial, I send the 8 bits of data one at a time. So 1 bit, 2 bit, 3 bits, 4 bits, 5, etc. And I have this clock that says, hey, there's a new bit available right now, right now, right now, right now. So that's a very simple serial protocol to have these 2 devices communicating. And I have just one line. You can see the advantages. I only have a single line instead of 8 lines. Asynchronous serial, which is really what we're using, is different from what I've shown here is synchronous, which means synchronous simply means there is a clock and everything occurs relative to the clock, synchronous to it. Asynchronous, there's no clock, and all you do is the sender and receiver assume the time base. So the sender and receiver say, we don't need this clock. Instead, what we're going to do, so this line is not here, is you're going to start sending, and every 1 millisecond, you're going to send me a new bit. So this is at 0, this is at 1 millisecond, 2 millisecond, etc. So we just use a known timing. This means that both sender and receiver need to agree on that. And this timing is called the baud rate. So you'll see this, in the lab, and you might have seen this elsewhere, where it calls out what the specific baud rate of the system is. There's a few other things that require definitions, such as what the parameters of how we're sending the data, if there's additional data to help us synchronize or detect errors. We don't care a lot about that for this class. I'm just going to sort of show you how to set it up such that it works with the computers, and you can do this with your laptop too. But if you're interested, I really encourage you to check out something like this tutorial that goes through more details of serial communications. As a note, if you get the baud rate wrong, so if you tell one side, hey, expect a new bit every 1 millisecond, and the other side is sending a new bit every half a millisecond or every 10 milliseconds, the data is going to be corrupt. So you'll see some sort of garbage for what we're using. There's all these really weird characters that make no sense. This is typically what you see. It varies a little, but you just see all sorts of garbage. And that almost always means you have the baud rate set wrong. If you were doing this with 2 separate devices, your board is luckily already set up for everything, so you don't need to do a whole lot. The only real thing to note is you notice the transmit pin of 1, so the pins are always relative to the device. The transmit pin of 1 goes to the receive of another. So there's two wires. One wire is sending data to the device, one wire is receiving data from the device. So in our system, this would be like the AVR, and this is part of the programmer board. It has the interface, which then brings it over USB to your computer. And they're sort of interconnected like this. The transmit goes to receive and receive to transmit. All right, so how do we use this in your device? Basically, this serial port is what the data is going to go over. So you'll have the printf. This top part here is the AVR, and the bottom part here is the, above this, which is computer, and the programmer board. But in our case, we just care about what's in the AVR. So we have the printf. The printf will take the data, make a string out of it, send it to this driver. So the driver is some software running on the AVR. The AVR sends it out over the serial port hardware. The other side of that, it then receives it, the USB to serial. So this is receiving it as a serial port, packaging it over USB. And finally, you have what's known as a terminal emulator. And the terminal emulator is where you can see the data or even send data back to the microcontroller. So what this means is that you can now dump values directly, or you can test program flow, and you can even set it up to let you, send data back to your robot. So if you're tuning a value, you don't have to reload, reprogram. You can just type in the value you want to be set. So as an example, the previous system, I might do something like this as a first test. So I have this printf that just says, now I'm driving into wall, now I'm driving left. You can use this, you can make it say the function name, tell you what arguments you're passing it with. And in this way, it's always just going to print what it's doing, and you don't have to use this LED code anymore. And you can leave these statements in if you want, and add more and come back later and stuff like that. So you have tons of flexibility to figure out what you want to do. There's sort of a special note, and you'll see this in the lab with printf on AVR. The AVR microcontrollers, so they have both what's known as SRAM and flash memory. The flash memory is for, so you see this flash program memory, is for instructions it's executing. You have quite a bit of that, so in this case 64 kilobytes of flash memory is on the chip, and you have a very limited amount of SRAM. So that same chip has 4 kilobytes of SRAM. SRAM is what's used to hold variables and stuff like that. So for your program, the 4K should be enough for fairly basic things. Even some more advanced work can be done in 4K of SRAM. The only caveat is that if you do stuff like this, so if I say printf and some string, what the compiler is actually doing is it stores. So in the code memory, this is good. It stores, in addition to the code, the printf instruction and all that stuff, there's the hello there, my friend. So this string. We have tons of code memory, we don't care. On startup, because technically this is classified as a variable because of how the C code standard works, the compiler is actually going to go ahead and copy that right into your SRAM buffer when the device turns on. And it's just going to stay there, and it just wastes your SRAM. If you only have a few printfs or they're small, you don't really care. If you're using tons of them, this is going to be an issue because you're now going to fill up this SRAM, and it's just with these useless strings. You don't really care about them. So what you'll see in the code is this kind of weird looking notation where we have this printf underscore p. So the underscore p is a special version of printf, and it requires you to use this pstr program string macro. And basically this setup here will force all of that data to only go into the flash memory. So it will no longer do this copy. It's always going to reside in code memory, and it's just going to read it straight from there. So if you want to use a lot of printfs, you should be very cautious of using these, especially if you're printing lots of status or data like that. But we'll see how we see what the current usage is and how we do that in the lab. I guess before that, any questions on the printf stuff? Does that all make somewhat sense? You'll see this in the lab. You'll have a chance to experiment. So, yep.
Do you need the PSTR?
Yeah. So if you don't have the PSTR here, if you just use the underscore P, it will actually cause an error because there'll be this mismatch. It'll think it's in the underscore p function thinks you don't need to copy it to RAM. The compiler will still copy it to RAM, and you'll end up with a problem. So if you don't, if you think you might not remember it, just use printf as is and do that. And you can then go back and change them to the underscore p. But that's another possible bug that you could get into. Okay. So I just wanted to review very quickly some common C errors. As a note, the PC lint, which I showed you in lecture number 1, and you'll do on the assignment on Thursday you'll get, will catch a lot of these errors, but so you're aware of them. Using equals instead of equals equals. So with C, this is the compare, and this is the assignment. The problem with C especially is that what I have here is actually a completely valid piece of code if x equals 6. What the C code will do, it's going to take 6 and assign it to x. So what I wanted to do was say, does x equal to 6? With this, it's going to assign 6 to the value x, and then if x is not equal to 0, this if statement will execute. So this if statement is always going to execute, and the value of x will be assigned to 6. So that's a really easy mistake to make, and most of the time you don't want to use this, you always want to use the equals equals. So lint will catch that pretty easily. So fixing would be to change that. Off by 1 errors are always common. So as an example, if you have some array, it can be confusing occasionally. When I define the array here, you notice this is a 16-byte array. But the maximum value of it is always just some array 15, not 16. So we never assign some array 16. When you're doing these loops, it can be hard to remember, if you put this as smaller than or equals to 16, what you'll end up with is some array 16. It'll get an invalid assignment to it. So off by 1 errors are another very common thing in C, and if you're writing an array and you're not sure of it, you should stop for a moment to think, what is the maximum value that I'm going to be indexing here? And if you're not sure, you can also try to fire the code in through lint. Again, it's pretty good at catching this type of stuff. Loop error, so the error here is this for loop. What's going to happen is it's not going to assign these values to some array. The problem is that I have this semicolon at the end of the for loop, and the C code will actually say, all right, you want me to just loop on what's between the end of here and the semicolon. So I'm just going to loop 16 times, like that, and then I'm done. And then it's going to spit out of the loop. And it'll actually give you a compiler error because the I is not defined within this next block of code. Because the loop, the I is only defined within that for loop, and that for loop is only running until the end of that semicolon. So how you fix that is you just don't have that semicolon at the end. But that's another very easy mistake to make. You use semicolons most places in C, but don't put them at the end of your for or while loop definitions. Yeah, so the whole loop body is now just that semicolon. If you use case statements, don't forget that, in C, it's going to execute all the code in here first, and it only stops executing once it reaches a break. So in this case, it's actually going to print 2. When x is 2, it'll print F2 and then print F3. So you always have to have the break in between to say, okay, stop now, and do the rest of the code. All right, so that's some very, very common errors. All right, so moving forward. So this lab, just as a note, is based almost entirely on the 3204 labs. So if you haven't used the microcontrollers a lot, I really encourage you to look at these labs. So the one we're doing, a lot of it's based on this lab 5 US art here. So basically we're going to be going through using printf, seeing how it affects the system. And as a note, you'll have to check the board needs these jumpers soldered on it. So it tells you in the lab as you go through. If your board doesn't, you can either grab a soldering iron in the class to make sure you solder them like that, or ask the technicians to do it. For a lot of the lab, there's one part where you'll be using a terminal emulator that's on the system. So there's a whole bunch of setup you have to do. It says somewhere. Yes, there's a whole bunch of stuff you've got to go through and check, so do that pretty carefully. It's easy to miss something. You might find it useful for, oh, this link doesn't work here. There's a link in the other lab, but there's a YouTube video that goes through the setup of it, so it's actually for a slightly different lab, but most of the stuff is applicable. Let me just open it so I can show you what's applicable. So basically you'll be setting this up, and then later you'll go through and about here. So here I'm just showing how you set up all of the serial port stuff. So if you want, you can also just watch this to get an overview of what we're going to do in the lab again. This lab is not quite the same as the one we're doing. We're basically doing the second part of this lab. If you want more details on setting up the microcontroller board, so the first part of this lab just gets you to blink an LED. The first lab here goes through, you know, how do you power the board? How do you connect it to the computer? This has more detail basically than the lab I have. So this lab says, you know, click this button, set this up. So I'm going to be using basically several of these labs in the lab today. All the links are there, but I just want to make sure you're aware of that. And again, this lab has a video that shows you exactly where to click and what to set up, which might be useful. The only real difference is content. There's a bit of an easier, because you have the breadboards all set up, an easier thing you can do for powering it is you can apply 10, there you go. So you can apply, basically you set the power supply to around 10 volts. So you'll plug your board into the breadboard, making sure it all lines up. And then you can apply 10 volts. And you can either apply it, there's a power jack here, so that's what the other lab shows you. As an alternative, use clips that are in your design kit to put 10 volts right into this rail here. And that'll power up the board. Be careful because you have 10 volts on the breadboard rails, not 5 volts. There's a separate pin that gives you 5 volts in it. So if you want to power digital logic or stuff like that, you know, make sure you use that 5 volt pin because you'll blow up stuff otherwise. And this also applies, even if you plug in the jack here, these rails normally still have 10 volts unless you fiddle with some jumpers. So I kind of recommend just to be very careful of that. All right. So I'm going to skip the in-circuit. The other thing I will skip that slide. There's another type of debugging called in-circuit emulator. It requires a special hardware device to do it, which you don't have on your board, so you can't use in this class. But it's worthwhile noting there is another system you can plug into your device and see the value of variables within it. If you're interested, you can talk to me about that. I might try to run a quick tutorial or something on it. But as I say, we won't be using it, so I'll skip that part of it. Yeah, so that's it. Any questions on the either repository or debugging? Yeah. If not, head to the lab.